Good morning. Welcome to Krishna's class. In this talk, we look at the structure of open sets in arcade. Now, our objective is to define the right kind of non-negative linear function such that on CCRK, from which you can arrive at the Lebesgue measurable sets and the Lebesgue, the whole thing can be one. So eventually you will get on RK Lebesgue measure definite. Now with that we looked at some results already, or some notations we have introduced last time, and we said that the Lebesgue measure has the special property, namely that is invariant under translation. If you take a measurable set and translate it, then the measure of the original set and its translate are the same. Now this is one constraint that you have on the Lebesgue measure. I mean, these are all the kind of relationship between algebraic structure, topological structure, and so on. Okay, so translation is an algebraic process actually now. So that is the it has to be translation invariant, and this property has to be taken care of. We are completely trying to mimic our experience of developing Lebesgue measure on R, except that now we are going to craft the whole thing with the help of the Rees representation here. With that, we introduce certain notations, and let us just recall the last one that we introduced, namely we introduced this one. W we defined as set of all x belonging to Rk such that alpha I less than beta I. Sometimes it may be even less than or equal to, doesn't matter. Where psi 1, psi 2, psi n are the components of x. So x is our notation. This turns out to be the variable. So in short, what we are saying is we are taking the interval alpha I, beta I for I equal to 1 to n, then take the product in Rk. So you get a volume. So that is W. And in that case, we have, of course, just a caution. When this less than can be replaced by less than or equal to in anywhere in this set. Okay? So they are all going to be, represented or given the notation W. This is just a sample. Okay. Now what you have is, so there are a variety of possibilities. Any of this, for any I, this alpha I less than psi I can be replaced by alpha I less than or equal to psi I. And for any I, this beta I, psi I less than beta I can be replaced by psi I less than or equal to beta I. Okay, so there are several possibilities that arrive at, but nevertheless, what you have is this volume means this is actually the hyper volume. Okay, in k-dimensional volume, I'll put of W equal to product of now this is something that we will have to do. So when k equal to 1, this will become the length of the interval. When k equal to, it will become the length of the area of the rectangle, and when k equal to 3, it will become the length of the rectangular the volume of the rectangular parallelepiped. I'm sorry, the area of the rectangle and the length of the the volume of the rectangular parallel. Now for higher volumes, now you call it the hyper volume, or you write it as k-dimensional volume of Turkey. Okay, so this is the definition. Now we define definition for A belonging to R. See A equal to say alpha 1, alpha n, sorry, alpha k, and delta positive is set QA delta. This is the notation that you use. This consists of all those x for which alpha I less than or equal to psi I. That means this becomes alpha A becomes a corner point of this hyperbox. Okay, that you have psi I less than alpha I plus delta. So what you have is, this is a hyperbox okay, with a corner point A, and each edge having length delta. So in R2, this will be simply this. This is in R2. So you see that this is the point alpha, and this distance is delta. This is also delta. So this is alpha plus delta. Sorry, alpha, what you call alpha 2 plus delta. So this is the QA delta in R2. and the volume of QA delta is equal to delta to the power K. This is the volume that you have, right? Now, let us now start with the process of, partitioning the whole RK into grids. Okay, so we will have some grid lines, and what I mean to say is that we are taking R2. So this is R2. Make grid lines like this. Just graphing. This is what we mean by, so that you can actually approximately compute the area of any region using these graphs. This is a very standard techniques. So let us do that. Now, definition. For n equal to 1, 2, etc. 1, etc. Find Pn set of all x belonging to Rk whose integral multiples of integral multiples of 2 to the power minus. Okay. So this is the set that we will be requiring in our analysis. Just tell you what exactly is. See, in R2, this is R2. We take x to be x equal to alpha 1. Sorry, we take points x with the property that this is m1 2 to the power minus n, m2 2 to the power, where m1 m2 belong to what you call integers, right? So these are the points that we are considering. So this is actually set of all x equal to m1 2 to the power minus n, m2 to the power minus n, mk where M1 belong to Z. Or I'll confusion, right? So 2 to the power, see, when we take Pn, the length of the box we are, okay, the set of mesh points that we are going to take have coordinates multiples of 2 to the power 5. So when n equal to 0, okay, n equal to 0, you will get all integer points. Take R. So this is 1, 1, 1, 2, etc. All these mesh points when n equal to 0. When n equal to 1, you will get multiples of half. Okay. When n equal to 2, you will get multiples of 1/4 or 1 by 2 to the power 2 square, etc. Okay. And this way we are trying to take, fill this whole space with all sorts of points. So P and we classify these set of. Now we will define the boxes that we are going to find. Let omega n be the collection of two to the power minus n boxes with corners now this is the crucial definition of omega. So for example, when n equal to 1, you are taking in R2 for instance, you are taking all points with the coordinates which are multiples of half, integral multiples of, okay, and then you take the square with edge length given by 1 by. So you see that this covers the whole space. Okay, so this omega n will cover the whole space. So let us look at the properties of. The first property is this, which is obvious. If n is fixed, each x belonging to Rk is in one and only one member of that is clear because suppose you are taking R2, take R2, then see you have this Now you have one square is like this, the other one is like this, the other one is like this, the other one is like this, and so on. Okay, that these two edges are not included, but these edges are. So this way we would be covering the whole space. Okay. So every point in this space will be exactly in one of the omega ends. Okay. So that's the point. Now here again, what you have to see is this is the situation that you have. Let me just name that here. Okay. See, if you are working in R1, it is going to be the intervals with the left end included in the interval. So this is what you have. So if you are working in k equal to 1, then you are working on and so on. And here on this side it's going to be minus 1 by 2, minus 1, minus 3 by 2, and so on. So a typical interval is of this kind. Now you see you have the whole of R written as the disjoint union of intervals of the type k into the power minus 1. Okay, that is one edge. The other edge is going to be minus 1. This is going to be the interval. Now you see that any point you take, it is in exactly one of these intervals. In the case of R2, what we have is, we are going to have the regions of this kind, and you see that a typical box is of this type. This is the corner. Okay. So what you have when k equal to 2, when k equal to 2, and we take here we have taken n equal to 1. So here we also take n equal to 1 set. Then what happens is, each point is going to be something like, so what you have is the whole of R2 as see, m1 2 to the power minus 1, m1 plus 1 2 to the power minus 1 is interval cos is a typical m2 2 to the power minus 1, m2 plus 1 for. So these two intervals and take the cross product. So you get a rectangular box. Okay. With these two lines, this corner is included. These lines are included, but not the edge. Okay. So this is the setup of this. Now you see that you are going to adjoin to this one, so this and this one, and you take the union of all this. So M1, M2. This way, Z square. This is the union. Again, this is a disjoint union. So you can write this. So you see that each one of this is a rectangular area or a square in R. Okay, with n points well marked out. That's the whole idea, and you can generalize this to the next level and so on. Okay. Now the second property that you have is Q prime is in omega n. That means having edge of length 2 to the power minus n. And Q double prime is omega r. This is again 2 to the power minus r. Edge 2 to the power minus r. And r is less than n. Then this is important question. What you have is Q prime or either this or Q prime intersection is empty. What does it mean? That means you see that either this interval, okay, and when you take, for instance, k equal to, sorry, n equal to 2 and r equal to 3. Okay, take r equal to 3. Then what happens? This condition is satisfied. Sorry. Okay. Then r is less than, this condition is satisfied. Now you see that if you look at the relationship between Q prime and Q double prime. Q double prime is in omega 3. And Q2 omega 2. And Q double prime, Q prime is in omega 2. Then what is the relationship between Q and Q3? What you would get is that Q double prime is contained in Q double prime, or the two may have empty intersection. Because if your Q is going to see, for instance, let me take a specific situation. Yeah. So we are once again working in scale equal to 2. Then you have Q prime is of the form power this is it. That is Q prime. What about Q double prime? Q double prime is of the form M1 prime This is the one. This is typical. Now, you see, this is the case when n equal to 3, r equal to 2. Okay. So, you see that, see, this is in R is less than n means R inverse is greater than n inverse. Okay. So, what does this mean? This means Q double prime is a bigger box than Q prime. Okay. So 1 by n, 1 by n. So you see that the length of or the volume of Q double prime is certainly what is the volume of Q double prime? Equal to, in this case, it is going to be 2 to the power minus 2r. The other one is going to be volume of Q prime is going to be minus Tn. These are the volumes. So the possibility that you have is that when R is less than N, you have the Q prime is a smaller box in magnitude compared with Q double. And what happens is Q prime is contained in Q double prime. This is one possibility, provided the endpoints are suitably chosen. But if not, either this whole Q prime is inside Q double prime, or Q prime is outside Q double prime, so that their intersection is empty. Now this is the scenario. See, in the case of 1, it is easy. In case of 1, what happens? You take 1 by 2, 1 by 2, etc. And then you take 1 by 4, 1 by 4, etc. Either this, see this interval is either contained in this, or even if this is interval, this is contained in this. So you take an interval of length half, then you take intervals of length quarter and quarter. So there are two intervals lying inside this, or any other interval of length 1 by 4, and the interval with or this given interval with length half are going to be disjoint. So either it is completely inside this or outside. This is the point. Okay. Now let me. So that must be. It's very easy to work it. It's easy to prove also, because once you use this coordinate representation, it's quite easy to. Okay. See, these are all obvious things. This is straightforward, because you are working in the k-dimensional space, and each edge has length 2 to the power minus r. Therefore, the volume is 2 to the power minus k. So that is clear. If n is greater than r, then what are Pn? Pn are the corner points. Then Pn has exactly the power n minus r times k Okay, so what you have is this. Okay, let us take the case of 2. Then what happens? Suppose n r equal to n by 2. Okay, suppose r equal to n. Then what happens? You are actually, this is your q. This is your q. Then you are dividing it into 2 parts. Okay. So how many points will be there? N minus R, N minus R, right, okay, and times 2 that you have. Okay. So how many points will be there? For instance, when you take n equal to 1, then what happens? You will have, so otherwise what happens? You have subdivision. Okay. Suppose there are so how many points would be there? N minus R is going to be n by 2. N by 2 times k will give you n. So if you are starting with q in omega r, then volume of this is 2. If n is greater than 1, then Pn is the number of points of the corners and is exactly 2 minus Rk points it. This is quite simple to verify. Okay. Now we work on this. It's easy to compute this. For instance, when k equal to 1, you are going to have to take what is it? N and n by 2. And you are going to have 2 points. Okay. You take n and n by 2, you are subdividing it, so there are 2 points. So this is what you have. Besides and this is the one that you are taking, and this point is there, this point is there. There are 2 points. But suppose you are working in a rectangle, then what you have? This point, this point, this point, this point, then this point won't be there. So these 4 points are going to be inside. So that's how the number of points will come, and that is given by this particular formula. That's easy to see. It's not difficult. Just a combinatorial, simple combinatorial result. Now the crucial property is this, and this is the one that we are used. I mean, these 3 are obvious. So every non-empty open set is a countable union of disjoint boxes this collection. Okay. Now we give the proof. This, of course, you need to use that it's an open set, and then some topological considerations are required. But otherwise, even that is straightforward. So let us work. So the statements another 2. Just straightforward. We have already described. Now we shall prove that means every open set, every non-empty open set with RK is a countable, disjoint boxes belonging. See, essentially what you are saying is this. Okay, so you have this kind of breaker. Okay, and then you refine this further. This is what you are doing. Every stage you are refining the subdivision, and then again each one of this you are refining, and so on. So what happens is you have look at the boxes inside this belonging to omega 1. They would also contain boxes belonging to omega 2. Just remove those, and then if then what you do is you go to boxes containing omega 2. From that you remove all these omega 3, omega 4, etc. such small boxes and so on. This is the strategy. So you can finally get. So what you are doing is the edge. What happens is this particular box does not cover this one. But you see that if you subdivide this box and this box covers that. So this box covers that. So 3 parts will be covered by that. But this is still not covered. So you further subdivide. And then you see 3 parts will be covered. Then again you subdivide that little box and so on. And get the union. So this is the strategy. I'll put it this way, easily. It's a better picture. This is what you have. Suppose this is the boundary of V. And you take a box somewhere at the corner. Okay. Now this doesn't cover that. So what happens? See that these boxes are that you accept. That's a larger box. Now neither this nor this portion is covered by these boxes. So what you do? Subdivide. Then you see that this is fully there, this is fully there, this is fully there. And if you take this, none of them is there. If you take this, none of them is there. Okay. So what happens? What is the next step? The next step is you take this one. Subdivide. So this is there, this is there, this is there, but this is not. And if you subdivide this, what happens? See that this is there, but these two are not. Okay. Similarly, you do with all these which are partially covered, and then take the one which is not covered, subdivide, and then you get. So each stage you get omega 1, omega 2, in omega 1, and then in omega 2, then in omega 3, then in omega 4, and so on. So you can eventually cover the whole of V using this kind of. That is the idea. So let us prove this. Let open the system. Okay, non-empty. Okay. Now you take X belonging, take an arbitrary X belonging. So what can you say about V? X is in V, V is open. Since V is open, a delta neighborhood of X is contained in that is coming from openness. Okay, that means a ball of radius delta is contained where delta is positive. Because here delta is positive. Therefore, what you do? So, having got this, see, you have an X, you have a delta neighborhood. Now, what you can do is you can have some box containing this. All that is you need to choose the because you can always choose 2 to the power minus k less than the radius of this. Okay, so that a box is inside. Okay. Belongs to Q for some contained in omega. This n you will have to choose appropriately depending on the magnitude of delta. Chosen in relation so, but what is clear is that there is some omega, some q which contains the point x and is inside. So q is contained, x belongs to q. This is the point. Okay. Now that's in omega. So V is the union of all these all boxes which lie in V and belong to some omega. If Q gets closer and closer to the boundary, then possibly you would need this n to be considerably large. Now, from among these boxes, select all those which belong to omega 1. There may be none. Okay, there may be none sometimes. And remove from these boxes all the boxes belonging to omega 2 etc. Because you can take the whole of that box once it is inside V there. Okay. right? And then in that case, you remove all the boxes that are inside which belong to omega 2, omega 3. That is the smaller boxes that belong. Now, from the remaining collection, select those boxes in omega 2, omega 2, which and then what you have to do is you remove all boxes inside omega 2, sorry, inside the boxes in omega 2. All those boxes in omega 3, omega 4, etc. In your. So you know that these boxes, the boxes in omega 2 is entirely contained in either in boxes in omega 2 or omega 1, or they do not belong to that. Or so you have this property. Now proceed in this way. We have in the A and B, that means we have done full complete boxes that are inside this from omega 1, then complete boxes which are there in omega from omega 2 but not inside those boxes in omega 1. Then we take omega 3 boxes in omega 3 which are inside V, but at the same time not in the boxes in omega 1 and omega 2 that we have already chosen, and so on. So you repeat this process, because you see that no matter how close a point is to the boundary of V, there is an open neighborhood of that inside that because of the openness. Therefore, you can find by choosing n sufficiently large, you can get an omega n. So in this way, we can write the V can be written as the disjoint, a countable union of disjoint boxes belonging to omega 1 union omega 2 union. So that is the. Okay, so we stop here. And now we are in a position to take up the construction of the defect measurable sets and share on us. Thank you very much.